Let me read you a statement. On tomorrow's exam and subsequent exams, right underneath the exam caption and immediately before the start of the problems and questions, there is a directive. The directive so far has read, enter the correct form code or else we'll charge you 10 points. Well, that's been nothing but an empty threat. As mad as I might get because you don't put in the form code, I'm not going to take off credit for that because I'm trying to find out what chemistry you know. Maybe I'll thwack you with a rubber band or something like that. I've changed the directive simply because on occasion, no matter how hard I try to avoid such, I'll make mistakes. And oftentimes, I don't recognize these mistakes until after you folks have been subjected to the exam. So here's the new directive. When you deal with the exam, I expect you to read it. But I'll read it to you now anyway. Enter the form code on the answer sheet. That's standard practice. Answer sheet AS. Note, respond to each question. I expect you to do that. But if you think the correct response, CR, is not provided, that's where I've made the goof. On the reverse side of the answer sheet, indicate the question number and write the correct response. Because it strikes me that the only way you can answer such questions is by coming up with what you believe to be the correct response. So if you're convinced your answer is correct, and I've not provided this among the answer choices, maybe I made a goof. Just turn over the answer sheet, because the machine that scores it doesn't look at the back side of the answer sheet. So you can write anything on the back side that you want. That's what the directive says. Mark the question number, so I know which question you're talking about. And write down what you think is the correct response. Like if it's a calculation and you're supposed to get a K value of 10 and I've not provided 10, and it's question 8, you write question 8, K equals 10. And then, after the exam, I'm not going to go through and look at the answer sheets. But if after I post the key you still think you're right, then you can come back to me and say, please look at the answer sheet, which I will. And if you're correct, you get credit. And I expect a few points bonus. Why not? I don't want to create these dilemmas. I assure you I make no mistakes in writing the exam on purpose. But these damn multiple choice tests are, this kind of stuff doesn't happen with real tests. But with multiple choice format it does. Are we understanding this?
So that's just for like rare cases.
That's for a case where you think you've got the right answer and I've not provided the right answer among the choices. Okay?
You've written an answer that you think is the right answer. Right?
You, meaning you. You're puzzled by this, aren't you?
Well, it's just making sure it's not like an F for every question is there's no correct answer present. Never mind. I think I can.
I'm not going to accept you think there's no correct answer present. So you write that for every question, which will tell me you don't know what you're doing. Because if I make these mistakes, which I have, I don't think I'm going to make them for every question on the exam. I think that's a fair statement. I'd hate to flunk my own course that poorly. All right, on we go. Use application of Nernst equation. We really showed you last time what the nuts and bolts of the Nernst equation are. The rest of it really lies in understanding what a question asks you to do, no more, no less. We've looked at this cell reaction in the past. For this cell reaction, E0 cell is plus 1.10 volts, which of course comes from coupling the zinc, of course, being oxidized to hydrated zinc ion half reaction, with the hydrated copper ion being reduced to copper metal half reaction. No more, no less. And for that system, it's the hydrated copper ion, copper half reaction, which, relative to the way it's written in the half reaction table, is the one that gets reversed. So it's the half reaction for which you change the sign on E0. We've been through this. That's all part of how to couple the half reactions. All right? Let's consider this system being treated throughout with 1 molar sodium sulfide solution. And one other question, is this a system where physical separation of the oxidizing half from the reducing half is required? If you construct this cell, must you physically separate the oxidizing half from the reducing half? For example, that's not necessary in a lead storage battery, because in a lead storage battery the reducer is lead metal, it's not in solution. Of course, in this system the reducer is zinc metal, it's not in solution. But in the lead storage battery, the oxidant is lead dioxide, which is also not in solution. So keeping lead and lead dioxide separate is easy. Just don't have them in contact with each other. That doesn't mean each half cell has to have a separate electrolyte system. But here, each half cell has to have a separate electrolyte system. Why? Because in the cathodic half cell, its electrolytic system, its solution electrolyte contains this stuff, doesn't it? And that's the oxidizer. So if you have this in contact with this, you've got a short circuit. So here you must physically separate oxidation and reduction. There's a statement about this in the notes that really was not written clearly when I first wrote it. Because this is one more thing which you try to learn about these damn cells and how they operate, and you can't pry it out of textbooks. Because I'm pretty sure they, like me, along the line, have not recognized how the cells really operate. But I said I'm going to try to figure this out. This is top of page 2218, writing net cell reactions for voltaic cells. When I first wrote that, I thought that it was required to physically separate, for every electrochemical cell, oxidation and reduction. That so far is true. The question is, can the oxidation and reduction half reaction system be run in the same electrolyte solution? And the answer is in many cases yes. Because the oxidizer, the reducer, the oxidation product, the reduction product are not necessarily in solution like the lead storage battery. Here, physical separation is required. Because this is the oxidant. You put this in contact with this, short circuit. Redox occurs, but you're not getting any usable electricity out of it. All right, let's imagine we have this system in operation and we treat with sodium sulfide solution. Well, in that case, the anode half reaction will convert to this. The cathode half reaction will convert to this. And what does this do? It diminishes E0 cell relative to the E0 cell we had when it was the hydrated metal ions involved. Here it's the sulfides of the metal that are involved. Tell me, from this information and this information, by comparison, see this stuff? And this stuff? If with this information and this information, what would you respond to my question, how's the stability of this compared to the stability of this?
Zinc sulfide is less sulfide?
I agree. Why? Defend it. Now you've got to put your thoughts into words.
Zinc is more easily oxidized.
What is that?
Zinc is more easily oxidized.
More easily what?
Oxidized.
Oxidized? Is that what you said?
Yes.
Well then, if zinc was more easily oxidized in this system, E0 here would be bigger than 1.10 volts. It's smaller. So what's this telling you about the relative thermodynamic stabilities of the sulfides compared to the relative thermodynamic stabilities of the hydrated metal ions? Copper sulfide is more stable, isn't it, than zinc sulfide? If the relative stabilities of zinc sulfide to copper sulfide were the same as the relative stabilities of hydrated zinc ion and hydrated copper ion, this would have the same E0 value. Here the E0 value got smaller. And here you're reducing copper sulfide. Up top you're reducing hydrated copper ion. So it must be true that this stuff is harder to reduce. It's considerably harder to reduce than that. And it must also be true that this stuff is more stable than this stuff. Because if this stuff was more stable than this stuff, E0 would have still went up, would have been still bigger than 1.10 volts. Think about it. Now then, you can add them up to get the net reaction. In the net reaction, you're going to get hydrogen sulfide ion and hydroxide ion as reactants as well as products. Which means that hydrogen sulfide ion and hydroxide ion will appear in the numerator as well as the denominator of the Q expression. Unless you cancel them. Can they be legitimately canceled? The answer is, if hydrogen sulfide and hydroxide ion are present at the same molarities, can they be canceled? Because now in the Q expression, you'll have a given value for HS minus and the same given value for HS minus in the denominator. Can you cancel it then? You betcha. Same for hydroxide ion. Okay? So you got to pay attention to what's going on here. But remember, we've stated that for this system to operate properly, the half cells have to be physically separated. The top system. Do we need physical separation here of the electrolyte systems? We don't now, do we? Because this is the oxidant, and that's not in solution. All you got to do is physically keep this away from this. And they're both in the same electrolyte system. Interesting, isn't it? Just by changing the nature of the oxidizer from something that's in solution to something that's not in solution. So in that respect, this system rather operates like the lead storage battery, doesn't it? Here are the oxidation reduction products in solution? Hell no. This is not in solution. This is not in solution. You haven't dissolved any pennies lately when you threw them in water, have you? I didn't think so. Okay? So that means for this system, unless I tell you otherwise, you can cancel HS minus and hydroxide ion as reactants and products in a net cell reaction. Unless I tell you they're physically separated. All right? Oh, I forgot about this slate when I was in a hurry to write this. Let's go over here. Since this really follows from what we've so far done. Imagine that I look at a net cell reaction, which is just like this one, isn't it? Except that this one is run under basic conditions, and that one we're saying is run under acidic conditions. Which means here, where HS minus is our sulfide ion source, what's going to be our sulfide ion source in this system? H2S. So I run this system in acidic media, and I observe this E0 value. Different than this E0 value. So tell me, based on this, the stability of which of these sulfides have been increased to the greater extent? Not the stability, but instability. Which sulfide seems to have become less stable as a consequence of going from basic to acidic media? Did we seem now to decrease the stability of copper sulfide more so than that of zinc sulfide? Because this E0 value is greater than this E0 value, and here the E0 value corresponds to operation in basic system, here acidic system. Keep in mind, this stuff is all a bunch of thermodynamic stability info. All right, what we want to do then is to see if with this information we can calculate E0 for this half reaction. Now then, we'll start by following this directive. In Table 2, our half reaction table, we see the appearance of copper sulfide plus hydronium ion, electrons, copper, H2S, water. Of course, in the table this is written in the other direction. And in the table this has a value of plus 0.134 volts. Whereas copper, being oxidized to hydrated copper ion, has a value of minus 0.34 volts. Again, if I turn this around, I'm looking at copper being oxidized by H2S in the presence of water to make hydronium ion. So clearly this is an acidic half reaction system. E0 will be plus 0.134 volts. Is this telling us something immediately about the relative stabilities of hydrated copper ion and copper sulfide? Because what we're finding out is that if I oxidize copper to copper, a hydrated copper ion, I have an E0 value of minus 0.34 volts. But if I oxidize copper to copper sulfide by H2S, then I have an E0 value of plus 0.134 volts, which is more stable, copper sulfide or hydrated copper ion. Copper sulfide, hey, this has got a positive potential if nothing else. Copper going to hydrated copper ion is minus 0.34 volts, negative potential relative to the standard hydrogen electrode. Again, we're just reading this from a thermodynamic stability standpoint. That's all we're doing. And look at this. If I turn this one around and show the oxidation of copper in the presence of basic solution and hydrogen sulfide ion to again make copper sulfide as my oxidation product. Here, if I turn this around, I get a potential plus 0.76 volts. Here, again making copper sulfide from copper by sulfide ion source, plus 0.134 volts, plus 0.76 volts, a heck of a lot more positive, heck of a lot bigger number, don't you think? So all is this not keeping with our recognition from an acid-base chemistry standpoint? If I want to make a sulfide precipitate, I can sure as hell do it better in basic system than I can in acidic system, correct? The sulfide ion is a strong base. So the more acidic the system, the more effectively I attack sulfide ion. Nothing fancy about this. Or put another way, here to make sulfide ion available to react with oxidized copper and make copper sulfide, I got to break one HS bond. But here to make sulfide ion available to react with oxidized copper and make copper sulfide, how many HS bonds do I have to break? 2. Is that going to cost me more? All right. So then, all we're asking you to realize is that by coupling this half reaction as written with this half reaction as written, what E0 value will I get? It's on the board. What will I get? What will I get? I'll get 0.77 volts, won't I? Isn't that the half reaction? Isn't that the E0 value for the cell reaction of zinc reducing copper sulfide in acidic system? I told you that, in acidic system, acidic solution, E0 for that is plus 0.77 volts. And if I add these two together, in a common electrolytic solution system, hydronium ions cancel, H2S cancels, that's what I get, don't I? So, adding these together, E0 plus 0.77 volts, and for this is written, E0 is minus 0.134 volts. Can I calculate then E0 for this half reaction? Nothing fancy about this. You do the arithmetic. How will E0 for this half reaction compare to plus 1.4 volts? Because here we have the oxidation of zinc by sulfide ion, but it's taking place in basic system. As opposed to this half reaction, whose E0 value we're trying to determine, where zinc is being oxidized again to zinc sulfide, but in acidic media. Which half reaction is going to have the larger E0 value for sure? This one or this one? Which one? Which one? Yup! Basic system, right? Is it making a sulfide easier in basic system? So whatever the E0 value is for this half reaction, you better find it to be smaller than this number. If you don't, you did something terribly wrong. And students come around, well, look, here's the calculation. I don't give a damn what you did with the calculation. Your chemistry is wrong. This is chemistry class. You all know that by now. That's for sure. Okay. Question 22-24. Open up table 2. Look at half reactions 19 and 39. Tell me what you see to be interesting, or perhaps you would wish to say unusual, about half reaction 39. There are a couple of other half reactions similar to 39 contained in this table. For half reaction 39, what potential do you see written? Read the value. For half reaction 39, in table 2, what potential do you see cited? Negative 0.41? 81? Okay. Is that an E0 value? No. Because if I'm going to do oxidation in water solution, and I don't have some additional solute component other than hydronium ion or hydroxide ion. Those are my only solute components. If I'm going to run this half reaction under standard state condition, then I must have the hydronium ion 1 molar or the hydroxide ion 1 molar. Otherwise, I'm not at standard state conditions, right? One more example of why you need to know what standard state conditions require and correspond to. So this E0 value this E value you just read me is not an E0 value. So if we're going to couple 19 and 39 to get an E0 for the system, which clearly we must if we're going to apply the Nernst equation to this, we've got to assign an E0 value to this. What E0 value would you like to assign to this? I'm listening.
0.82.
Point what?
0.82.
0.82?
Negative 1.2.
Negative 0.88.
We're all looking at 39, aren't we? And we're looking in table 2? I got it on here. I don't see it there. I'm listening. What is that?
Negative 1.23.
Yes! You say why 0.40 is the correct value?
Reverse the reaction.
Is this system not running in basic media? Does this system involve oxygen as an oxidizer? Yes? So we want a half reaction in our table which involves oxygen as an oxidizer. There are a few half reactions in the table which involve oxygen as an oxidizer. And to realize such, you have to take the half reactions as written and view them in the opposite direction. And if we're having oxygen function as an oxidizer in basic system, and the source of the basic system is hydroxide ion, then at what pH must we be operating? 14, because that's 1 molar hydroxide ion, isn't it? Wonderful. So we got finally the correct E0 value. Plus or minus? Plus or minus? Are we taking the half reaction as it is written in the table, which is now half reaction, what's the number, 35? Yeah, 35. And we're writing that in the opposite direction, aren't we? So we change the sign on E0. There you have it. 1.16 volts is E0 for the cell. Do you see a number of, regarding this number of half reactions you see in table 2 that involve oxygen as an oxidizer? We've been through this before. Under what pH conditions is oxygen found to be the better oxidizer, the stronger oxidizer? Acidic, basic, or neutral? Ooh, I hear arguments in the audience. The jury is fighting with each other. Acidic, basic, or neutral? Under what pH condition is oxygen the better oxidizer? Look at the table. Because I think plus 1.23 volts is bigger than plus 0.40 volts. You agree? What half reaction am I now referring to? Which one? 40 what? 1. Because as written, that's got a potential of minus 1.23 volts, doesn't it? But we want to consider oxygen as an oxidizer. I have to look at that half reaction traveling in the other direction, don't I? Wonderful. We've done this before. Did we not find out that oxidation takes place more readily in acidic solution than basic solution, if nothing else counts? Was not zinc readily oxidized in 1 molar hydronium ion and not oxidized in pH 7 water? How about that? Now, if you want something to be a stronger reducer, so look at the half reactions involving hydrogen. Because each half reaction, as written in the table, which contains hydrogen, reflects hydrogen as a reducer. Under what pH conditions is hydrogen the most potent reducer? Acidic, basic, or neutral? Do you see basic? Good. Now I'll ask you another question. At home, you have food in the refrigerator. Food A is like spaghetti sauce or something like that. It's acidic. I trust you know that tomatoes are acidic. Food B is basic. I can't think of anything straight away. Not strongly basic. If you eat food that's pH 14, you're going to have a serious problem. You will have a case of upset stomach from which you will never recover. All right? We got acidic food, basic food. Which food will last longer? With no other factors being considered. Which food will more readily react with atmospheric oxygen? The acidic food or the basic food? Acidic. Sounds like the jury's hung. Which food will have the greater tendency to react with atmospheric oxygen, the most common oxidizer in our environment? The acidic food or the basic food? Acidic. Which is the better reducer? The basic stuff or the acid stuff? The basic stuff or the acid stuff? Which is the better reducer? Better reducer. The basic stuff, isn't it? Didn't we see hydrogen as a better reducer as it gets more basic? So which of these foods has the greater tendency to react with atmospheric oxygen and spoil? The basic stuff, doesn't it? How about that? Because it's a stronger reducer, with no other factors counting. Hey, I'm telling you what. I can open a jar of store-bought spaghetti sauce, take what I want, put the cap back on, and that keeps for a long, long time. Don't try that with other foods, like cheeses, for example. It won't last very long. So now you can run home, make a water slurry of cheese and measure its pH. And I'll bet you $10 to a donut, it's certainly a more basic system than your spaghetti sauce. All right? So then, for this, can the hydroxide ions be canceled from the net reaction? For this system. Well, of course, if the hydroxide ion in the anode half cell and cathode half cell are at the same molarity. But here, the reducer's copper and the oxidizer's oxygen. So what do I have to physically separate in this system? Copper from direct contact with the oxygen that's bubbled into the system. Right? But I could have a plate in there. Each half cell can be conducted in the same electrolyte. As long as I don't have this stuff touching this stuff, I won't have a short circuit. Is that all right? Now then, one more question. See this half cell 39? There are a number of half cells or half reactions, if you prefer, on our table. Does this half cell, in order to be used, need to be outfitted with an electrode? What's an electrode? What is an electrode? Did you read the notes attached to the half reaction table? Did you read them and understand them? Did you not recognize this information directs you to realize there's a number of these half reaction systems which must be fitted with an electrode? I'd like to see you connect a piece of wire to hydroxide ion or water molecules. Come here, water, I want to put this wire on you. Or better yet, the oxygen gas. Can you connect wire to that stuff? Here's oxygen. If I give you a piece of wire, can you go connect some oxygen to the wire and keep the contact maintained? Huh? No. So such a half reaction system has got to be outfitted with an electrode. What's an electrode? It's a current carrier. You believe that? Why else would we call it an electrode? Something I can connect a piece of wire to, and something which will conduct electricity. What properties do you think you'd like to have an electrode exhibit? How about a stick of sodium metal? Would that capable of carrying a current? Sodium metal? Damn right. Want to use a stick of sodium as an electrode? Bomb! Oh, damn it! I shouldn't have used sodium. Just blew yourself up and everything else. So we want a current carrying device, solid, and inert or reactive? Inert. Upshot. Platinum is a very commonly used electrode material, but it's expensive. Platinum is far more expensive than gold. But carbon graphite often will fill this purpose nicely because it's a conductor. Remember when we talked about carbon graphite? Resonance, conductor, and quite inert. Good stuff for electrode. All right. Question 2225. Oh, by the way, if you do the arithmetic on this, for the stated conditions that are indicated in the notes, you'll get, after applying Nernst, E cell equals plus 1.108 volts. So under the called for conditions, this operates at a potential somewhat lower than E0. You can do the arithmetic. 2225. Again, a very common use of the Nernst equation is to serve the purpose of calculating values for K, equilibrium constants. So let's imagine I wish to calculate the KSP equilibrium constant for this semi-soluble stuff. Now notice that this is iron in the +2. This stuff contains iron in the +2 oxidation state. In a laboratory, for those of you who get to assignment 10, you'll do some work with iron in the +3 oxidation state. So regarding our laboratory work, you'll use iron in the +2 oxidation state for only one purpose. Anybody remember what it is? For what purpose in 46 laboratory do you use iron in the +2 oxidation state? Nitrate ion test. By golly, that's it. For the iron +2 serves two purposes. It reduces nitrate ion to NO, and then it complexes the NO to form a brown colored complex ion, which you see in solution on the top of the surface of the ferrous ammonium sulfate crystal if nitrate ion was in the test solution after you triggered the reaction with some concentrated sulfuric acid solution. All right? Now bear in mind what this question is really asking you is, do you remember the reaction which corresponds to KSP? Or specifically for this case, what reaction corresponds to KSP for this stuff? Do you see this reaction in your mind's eye? If not, you may find it beneficial to write the reaction, the chemical reaction, for which if you measured K, you'd get KSP for that stuff. Write it on your paper. What are the fundamental ion components of this stuff? What ions in water solution react with each other to make this stuff? Hydroxide ion. And what is the iron-containing ion that reacts with hydroxide ion to make this precipitate? Hydrated iron plus 2. Because without this information, you are not going to know what half reaction to select. Now this is not an equation, but it is a skeleton. You'll find out that part of the skeleton you're going to need water over here. You turn it into an equation. Let's get on with deciding on the half reactions. Look at table 2. Tell me the half reactions and tell me which of these half reactions gets reversed in the coupling process so that when you apply inerts, you'll calculate KSP for this semi-soluble material. I want to know the half reactions and I want to know which one gets reversed. Anybody got a number to pick? 17. I heard 17. Other numbers? 21. Other numbers? We're looking at table 2, the long table, it's in the notes. Tell me the numbers. 22. Well, clearly we got to have an error. There's only got a couple 2 half reactions, right? And I'll give you this hint. These are both wrong. 37. I'll strike that one too. 15. All right, we got them. Now then, 15 and 22. Which one gets reversed? Can't be both reversed. I want to put these half reactions together so that when I add them up, I get this. Which one gets reversed? Good. And when I do this, what will be the value for E cell? 0, because the system is under what conditions? What conditions? What conditions? Am I calculating an equilibrium constant? So under what conditions does this system exist? Equilibrium! When the system's at equilibrium, delta G is 0, which means E cell is 0. And you take it from there. The value you will get if you do the arithmetic correctly is 1.2 times 10 to the minus 15. Now there's a couple things we have yet to talk about in chapter 22, but that won't be on the exam, so don't worry about it. We'll do that next time. And after you